Okay, I think we'll go ahead and get started. Welcome, everyone. Really appreciate you joining us today. I'm Randy Sandone. I'm the Executive Director of the Critical Infrastructure Resilience Institute here at the University of Illinois at Urbana-Champaign. The presentation today will be a panel on protecting connected cities of the present and future. And we have quite a good lineup today, and our moderator is really a very interesting individual with a tremendous amount of experience in this space, and really looking forward to a lively panel and some information. By way of introduction for those who don't know us already, as I mentioned, we are a DHS Center of Excellence. We are funded out of the DHS Science and Technology Directorate's Office of University Programs. And our mission space is to conduct outputs-oriented research and to engage in technology transition initiatives to get those outputs into the field, as well as engage in education and workforce development initiatives to ensure our workforce has the knowledge and skills needed to address today's and tomorrow's critical infrastructure resilience challenges. And all of those missions have one objective, and that is to strengthen the security and resilience of our nation's critical infrastructure. Surprise, surprise, it's in the name of our institute. Well, telecommunications, especially wireless and mobile, the mobile sector is increasingly important to almost every other infrastructure sector. And this will be ever more so as we move to 5G and Internet of Things. And it is therefore particularly critical as we migrate our cities to smarter and smarter technologies, and many of which will rely on 5G and IoT. So it's a major focus of research for us here at CIRI, and it has been over the last year or so, and we're going to be going forward because of its criticality. And so our panel today, which includes academic and industry researchers, will discuss the importance of security and resilience in the wireless and mobile comm sector, and how their project is addressing at least a portion of the problem. We're not addressing all of it. That's a very significant task. We are addressing significant and challenging areas in attacking the problem. But there's a lot more work to do. In any event, this will all be brought to fore here with our panel moderator, Joseph Reitano, and I'd like to introduce him. Joe is an artificial intelligence researcher with the U.S. federal government, as an experienced machine learning and artificial intelligence researcher with a demonstrated history of applied computer science, working in information technology, transportation, energy, military, government industries. Joe's highly skilled in computer forensics, information assurance, cloud security, machine learning, intelligence, and data science. He's a strong research professional with a PhD, ABD, focused in computer science and artificial intelligence from the University of Tennessee, Knoxville. With that, I'd like to let you take over, Joe. Welcome, and thank you very much for serving.
Well, thanks so much, Randy. Hi, everyone. I'm Joe Reitano. I work in the AI Centers of Excellence. We look at trying to enable AI capabilities across the federal government, and thanks so much for having me today. I'd like to introduce our panelists. First up, we've got Glenn Sallow of Synclesis. He has a master's degree in electrical engineering from the University of Illinois. His principal areas of technical expertise are in electromagnetic phenomenology, computational methods, antenna radar systems, software development. And throughout his career, Mr. Sallow has supported a broad range of engineering development programs for high-power microwave weapon systems, EMP, missile defense, foliage penetrating radars, radar signature management, and electronic survivability. Next up is Karthik Subramanian. He's the CEO of Karthik Consulting. He's got a master's degree in computer science and has 25 years of experience as a technology consultant and architect for various private sector companies and government agencies. Next up is Walt Magnuson, Director of iTech. He's an experienced Director of Telecommunications with a demonstrated history of working in the higher education industry. He's got a strong information technology background, skilled in analytical skills, enterprise software, team building, IT strategy, and public speaking. He hails from the Texas A&M University. Next up, we've got Junaid Farouk. He's an assistant professor at the Department of Electrical and Computer Engineering at the University of Michigan Dearborn. His research interests include modeling, analysis, and optimization of wireless communication systems, cyber physical systems, and Internet of Things. He has a PhD in electrical engineering from the Tandon School of Engineering, New York University, Brooklyn, New York. And last but not least, Guoyang Zhu. He's received his electrical engineering degree from McGill University and from University of Toronto, PhD from the University of Illinois, Urbana-Champaign. After stints at Princeton University, he's currently an associate professor at NYU. Alrighty, so that's our all-star cast. We can move right on to our first presentation. Glenn, take it away.
All right, good afternoon, everyone. I'm Glenn Salo with Synclesis Incorporated. I'm going to talk to you today about a project we're working on with CIRI for assessing EMP risk and trying to mitigate those risks. This is a project that Synclesis is performing in conjunction with a team from the University of Illinois itself. So next slide, please. So EMP, for those of you who may not be familiar with it, occurs when a nuclear device is detonated above the Earth's atmosphere, typically very high above the Earth's atmosphere, 40 kilometers or higher. When this occurs, there's what we call an extreme electromagnetic field that gets caused by that nuclear detonation. And that detonation, that electromagnetic field, then radiates across a region. And depending on how high that detonation is, it can cover very large regions of the country. For example, from the graphic here, if the detonation was 30 miles above the Earth's surface, it would cover 5 or 6 states in the Midwest. But if it gets to 300 miles above the surface, it could essentially cover the entire continental United States. And so this leads us to a situation where a single detonation high above our country could impact a very, very large geographical area of our country. And this impact can be something that can either damage or disrupt or destroy power grids, communication networks, or anything with electronic systems. And that could lead to a very bad state within our country. Just imagine even half the country being without power. You can't get fuel, you can't get food, you had no communications. It could very quickly go into a state of anarchy. And so looking at EMP is something that's very important. Next slide, please. If we think of the EMP, thankfully, it's a low probability of occurring. At least we believe it is. But EMP itself, if it does occur, has a very high consequence. And so we look at this as a low probability but high consequence scenario. There's many challenges, as you can imagine, with dealing with EMP and trying to assess its impact on electronic systems. Part of the problem is that it's very difficult to test. We don't go out and detonate nuclear weapons above our country to test what's going to happen. In addition to that, there are significant uncertainties, how high it's being detonated, what angle it's impacting different systems. The system's response to EMP vary dramatically, whether or not you have direct radiation or if it's coming through a power line, whether the system's operational or not operational, the power levels, whether doors are open or windows are open or closed. All those things really impact the effectiveness of an EMP event. And so it's very difficult to predict what's going to happen. In addition, EMP is a lot different than your traditional hazard, if you will. An EMP event can occur within, milliseconds or seconds. And so you imagine all the power going out in the country within seconds. That's very different than a hurricane or something like that, where we typically know in advance that it's coming, but even when it's there, you have a period of time. EMP is a sort of a very unique in this range of naturally occurring hazards or concerns that we may have. It's not naturally occurring, but it's a concern that we have. And as a result, there's been multiple, documents and organizations addressing EMP. This document shown here on the right, something that's developed by the Department of Homeland Security. There's executive orders, et cetera, all requiring our government to address the EMP risk. And so next slide, please. And so our hypothesis, which is actually proven out in the real world, is that EMP is something that you can prevent. This is an image here of a test facility in New Mexico. And the military routinely takes out equipment and test that equipment against EMP. They design it to withstand EMP events. This is very costly. Typically, it's only done on certain military equipment. Civilian systems usually do not require EMP hardening. And even still, with the testing and the current modeling and simulation capabilities that they have been using, they really have limited capabilities. You can't test every situation, you can't simulate every situation, and because of the complexity, they oftentimes make approximations, such as just everything power-based instead of actual waveform-based, and so the actual impact is very, very hard to predict. And that's exactly what we're trying to address in our current project. And so next slide, please. And so, as I alluded to earlier, EMP, the effect of an EMP event really depends on many, many parameters. There are system variables, how high the EMP nuclear detonation is, the strength of it, the relative angle to the system that's being radiated by the electromagnetic field, the operational conditions of the system that you're working with, but then also manufacturing. We're looking at an EMP that's radiating across the country, but we're concerned about the effects that it has on solid state devices. And so that means that the cables that are running to that device, the device itself, the manufacturing tolerances all impact what's going to happen at that device level. And the range of variation can be orders of magnitude. And so whereas one device of the same type might fail at a certain level, another device of the same type may not fail at 10 times that level. And so we're trying to develop a statistical method of analyzing the effect of EMP on systems. And so we can understand the probability of something being damaged or being disrupted. And we're trying to also evaluate the effectiveness of different mitigation techniques. And in this particular project, we're focusing our efforts on a communication system. There's many people in the country working on the power distribution systems. Right now, we're focusing our efforts on the communication system. And so next slide, please. And so this is just sort of a little graphic that illustrates what's happening in an EMP event. You have the radiation propagates, it couples to different systems. It can couple straight to a cell tower, for example, or it can couple straight to a power line. Once it's on the power line, that energy can propagate along a power line, and it can accumulate as it goes along because the other part of the power line could be being radiated by the EMP itself. It might go into a building. It's got to penetrate the building, get down to electronics. And ultimately what we're doing here is we're looking at the impact that an EMP event has on an electronic circuit. And so we're trying to look at the changes in the system performance. And so we can look at bit error rates or signal to noise levels or things of that nature from the system level. So now we can quantify the probability that any EMP event will have on specific characteristics of the system. So next slide, please. And so just to kind of wrap this up, there's this project here. We're actually trying to create a tool that can be used by the community. And so we have actually two programs going on. One's funded through the Department of Defense to develop a electromagnetic interference modeling approach. We're actually modifying that capability to extend it to supporting electromagnetic pulse type of applications. And then our goal is to actually commercialize this, turn this into a product that can be used by governments, by industry, and so on. And it consists of several different parts. It consists of a framework that pulls everything together, electromagnetic analysis, circuit analysis, propagation along transmission lines, and so on. It actually includes circuit simulators themselves as part of the whole package. And so last slide, please. As part of what we're doing here as well, we are working with industry, and we have letters of support right now, people who are interested in what we're doing, coming from the electronic design industry to people who make electronics that go into the cell towers, et cetera. The people who are developing computer-aided design tools. And so there's some companies out there that are developing engineering tools. They would like to integrate our capability into their tools. And we have support from the aerospace and the Department of Defense in terms of making this capability a reality. And so that's all I have right now for our overview of the EMP project.
Oh, thanks so much, Glenn. That was an excellent presentation and overview. Let's roll to the next one, and we'll save all questions till the end of all the briefings. Thanks. Karthik, you're up.
Okay, thank you. Hey, good afternoon, everybody. Karthik Balasubramanian. We are a small business. We've been working with the University of Illinois, the CIRI Institute for the last 18 months or so. And I'll summarize and give an overview of the project we just finished and how it impacts, relates to critical infrastructure, smart cities, etc. Obviously, the emergency communication landscape is changing, and so is the cybersecurity threat. 911 emergency communication centers, or PSAPs, are not only critical for the individual citizen safety, but also that's the national security, economic security, as we saw in the last summer about riots and other things happening and people not able to reach 911, etc. And also the infamous incident that happened, 2 or 3 years ago about the false alarm of an incoming missile from North Korea in Hawaii, wireless emergency alert system. So there are things that could happen intentionally or not, or sabotage, that could certainly affect a lot of different things. Next slide, please. And therefore, for the U.S. to be able to, for us to maintain the innovative technologies, we are, depending on the critical infrastructure, the telecommunication infrastructure, supply chain, they're very important. Like the Huawei incident that happened, where there are fake components, and I think there's another talk that's coming down that talks about supply chain in particular. And so it has to be looked at holistically, and also with the next generation 911 coming up, NG 911. The transition is happening from analog to digital. All the IoT devices, our smartphones, our Fitbits, our smart cars, all of these different things are all connected up to the internet, into the cloud, and they're communicating. We're moving from 3G, 4G to 5G, and so there's a whole new set of attack vectors that are coming up that could be exploited by adversaries. And so the public safety is directly threatened by the 911 system, or the emergency system like we talked about, and we need to be able to protect the entire telecommunication infrastructure, the supply chain of things that go into it, and also the cyber physical systems, etc., that are there. And therefore, because the future safety of our citizens and the economy actually depends on these things. Next slide, please. So as we talked earlier, just a little bit ago, the analog is going into more hybrid. Okay. They're going to hybrid, which means 911, E911, wireless things are happening. Quantum computing, where the internet is now exploding. You have the dark web, where you can go download all kinds of interesting stuff for a few pennies or a few dollars that can actually turn into kits that can be exploited. IoT devices, like we talked about, which are relatively insecure because they are meant for feature. They're open, they can talk to anything, they can receive anything, and they are hijackable and be used to route stuff back out to somebody else. From hundreds and hundreds or millions of devices, we are now going into billions and billions of devices. Same thing about moving to the cloud. Going to the cloud, unlimited computational power is available. You can spin up EC2 instances or Azure or thing in the cloud for pennies, that the computational capacity available to do these kind of attacks are now getting very, very cheap, right? You don't need to be a nation state or a big deep pocketed organization. You can just spin it up for a few $100s. And so that makes the threat and the possibility and the ease in which it can be done a lot more difficult to track and be ready for. Similarly, the shift that's happening in telecommunication from 4G to 5G, satellites, low orbit satellites, things coming up, or even software-defined radios, right? Earlier, with software-defined radios, you can frequency hop and go back programmable radios. So the attack vectors are many, many. And last but not least, certainly, with the new advanced AI, ML, natural language processing, quantum computing, this can be spun up and done by the billions or millions of attacks happening or simulated across to bring something down. And as part of our work that we just finished, we submitted the final report. We talked to several PSAPs, right? The public safety answering points or the emergency communication centers across the country, and we got firsthand reports or firsthand feedback on in the last summer how PSAPs were attacked, or the telephone denial of service, 911 emergency coming down, people not being able to reach, call 911, etc. And I think there was another event that some of you might have heard of through a Facebook page. Somebody was able to send out a malware, which when you went to that Facebook page, it behind the scenes started using your smartphone and making the 911 calls, and the person with the phone did not even know about this, right? So the attack is getting more sophisticated and being able to use this technology. Next slide, please. And so with the expansion, right, from the 911 ESAPs, we've already been exposed to cybersecurity challenges, and where the ECC can be a gateway, and now with voice over IP calls and 911 text messages, SMS, other kinds of technology are being added, whereby you don't need to, you can get to a 911 center by no longer just by phone, but by texting, by voice calls, E911 or chat messages, etc., etc. So that's where we are moving to be able to have video calls and no longer just phone calls, right? And like I talked about, we've seen telephone denial of service on the 911 centers. With the wireless networks and social media, internet stuff, like I said, the Facebook and other sites, all these dark websites start coming out. You go click on it, and the next thing you know, your phone is being used for tracking or sending something else, etc. And so this risk is real. It's present. It's here today. It's not something out in the future. And again, malware compromised are being used into these phones as messages. And so there's a lot of vectors that are happening. Attack vectors that we just have to look at it and be prepared for as we race into this adoption of technology and IoTs, etc. Next slide, please. So the attack surface is expanding, right, geometrically. That is, it's no longer just a phone call or a phone, but it's going in a much exponential way. So the three pillars of our emergency communication system, the NG911 ECC or the PSAP system, the wireless emergency alert system, and all the telecommunications supporting infrastructure and the supply chain, these are all critical elements of the national critical infrastructure, right? And the 911 system, the key is to be able to receive and respond to an emergency message in a high integrity manner. That is, we need to be able to know that the person who's calling is really a person who they say they are, or the location where we think it's coming from is a location that cannot be spoofed, or we know that they are. And when the response goes back to these people, that cannot be intercepted and something else is going back to these people, right? So that we know that the person that's really in trouble or needs help is the one that's being called, and they're actually reaching a 911 center, and the two parties are talking, right? And so with the internet, now you can spoof location, you can spoof all kinds of different things. So the person may not even be, it could be a bot out in Russia or in China or somewhere else that's sending out all these messages and text messages or chat or posts, whatever they are, and they could spoof it and make it sound like it's coming from somewhere else. And so the first responders now have to trust the integrity of the source, the location, the event itself, so that it's not set up or a trap, right? Things like that. They're not just being distracted. And then certainly, like I said, the integrity of the message, who sent it, technology is not AI or bots or something else that's making deep fake messages that are being sent out through these mechanisms, or some satellite is being used to send out that is not really a live or a real person. And then they're actioned and they reach the correct first responder and then go back to the right communication. And then these communication channels are actually available and operational. The availability aspect of the CIRI triad, right? The availability also very important, that it cannot be brought down. And therefore, the integrity and the security challenges for the emergency communication systems is not a trivial thing. They're all, the architecture as they move into this, and the scalability and the sheer quantity of devices that could be used is all part of this process that we are trying to study. And as part of our follow-on work, we are expanding and looking more into the NG911 portion and the interoperability among them, so that we can study that. Again, I'm happy to take any questions later on. Thank you. Yeah, I mean, okay, sorry. So the slide is about, like what we just talked about. The attack surface is expanding. Multiple channels are coming up, and from a lot more to do. One of the things we have done right now is that when we went through the talking to the PSAPs, what we realized was that they are really still far behind. Even some of the basic blocking and tackling from a cyber hygiene perspective is not there. Not that they don't want to do it, but they're all local entities, supported by local tax dollars. And so, real equipment to firefighters, to policemen, women, and others, the first responders, is obviously their priority, getting the better equipment, better gear. So that's really where any resource available goes towards that. And so we've recognized that there is a gap in the cybersecurity and the importance for it. And obviously we're trying to help educate them. And I think there are some efforts happening from CIRI to be able to expand this knowledge base, and we have some follow-on work, some recommendations that we've made on how we can help the PSAPs get into a process of knowing their maturity or knowing their cybersecurity maturity level, like the CMMC model, and then expand on it to go from, hey, this is where we are today, but here are the gaps. So the step one is to know where you are, and then based on that, they can develop a roadmap and go through a process and say, these changes when we make, we'll get to a higher maturity level. It might be lack of certain policies, create the policies, create procedures, start adding the auditing and the things that are needed so that we know what happened in an incident, we can go back and see. So it's just basically building that maturity model, whereby coming out as a country, DHS or whoever else can look across the country and see the security posture of the PSAPs, because that's the first line, right? That's where we call first. And so that's the work we are working on and following on up to be able to build and actually give them a tool that can be used by the PSAPs to measure their security posture, and then develop a POAM or a plan of action to say, hey, these are the gaps we have, and then this is the maturity level we are in right now. And then as we add more things and get the processes and procedures and tools in place and get better at it, then we will start getting higher up in the maturity level. So it's visible not only for them, but across the board, we are able to see the security posture of where our PSAPs, ECCs are, both from a legacy perspective or the NG911. And so that collectively, we at least have a baseline to talk about where we are. Otherwise, it's all, it's a very nebulous thing. And hopefully coming out of this effort, we will have a tool that can be used to track and know where we are and measure the security posture of the PSAPs. Next slide, please. Yep, thank you. So again, questions, I'm here. We'll talk after this. Thank you.
All right, thanks, Karthik. That was a great overview of some of the Herculean efforts that need to be undertaken for cybersecurity. At this time, I'd like to just ask everyone that's online and on the phone to go ahead and check your mute button and ensure that you are muted. We're getting a lot of feedback for the presenters. Elena describes in the chat that you can go ahead and use *6 on your phone to either mute or unmute your phone. So go ahead and double check that if you could, and we'll get to our next one with Walt Magnuson. Thanks.
Howdy, and good afternoon, everyone. Walt Magnuson, Texas A&M University. I direct the Internet Technology Evaluation Center, which has been working in public safety communications since 2004, primarily in the NG 911 space, and then also we've done a lot of work in the public safety broadband, what most of you know, but basically as FirstNet. So you know, we've been working in those two spaces pretty extensively, and talk a little bit today about what's going on in that space. You know, Karthik did a really good job of talking about cybersecurity and the threats and the issues and everything else with NG 911. But if you look at it, the majority of outages that happen to 911 are not created by cyber attacks. Most of them are created out of either man-made or natural disasters. So next slide. You know, cases in point, you see in the upper left-hand corner, as the fires basically roared through California last year. This is one of the sites there in Crystal Park, and this is actually a communications tower that this was a few minutes before the tower site pretty much went up in flames, and of course that had disabled quite a bit. Most of you that work with 911 understand that we use basically pretty much fiber-based networks to do the communications. A significant amount of the fiber that's installed across the country is installed over telephone poles and over power lines. And this is what a lower left comment it looks like in a hurricane scenario. Upper right, what you're really seeing there is this is a woman that was there being taken out of the PSAPs or the ECC. This one here happened to be in Puerto Rico, as you can tell from the flag. And that one is, again, COVID-based. So because of the spread of the pandemic and everything else, you know, they're dealing with staffing issues and, again, dealing with contaminated space and things like that. So COVID has started to cause some of the outages. And then really what you see on the lower right, that was actually the Nashville bombing. So with the Nashville bombing, what happened again, as I'm sure all of you know, basically a car parked in front of a building. That building happened to be pretty much a AT&T facility that also happened to be used as a carrier hotel. Problems with carrier hotels, of course, is they have a large amount of facilities in them. So when you end up in a situation like that, what you've really got there is a situation where all of a sudden I thought I had a primary link and I had a secondary link, but because of things like indefeasible rights to use, where one service provider is providing extra fiber to a second service provider, and things like carrier resale agreements, what you end up with is all of your eggs in one basket when you really didn't end up even really realizing it. And then of course, there's obviously equipment malfunction. Equipment fails all the time. I mean, there's no piece of communications device that's ever been built that's not going to break down at some time. So we've got natural failures, but then also a significant amount of the outages you see are caused by misconfigurations. There were a couple outages over the last year that actually lasted several hours, where in essence a routing change was made at the wrong time and caused information to basically, or 911 calls to be black holed. So there's a number of different threat vectors. So how do we protect ourselves from these threat vectors? Next slide. Oh, I'm sorry, by the way, this one shouldn't be in there. I forgot to take it out. Okay, so what can be done? The first one really basically is in next gen 911 conversion. Now, why does that help eliminate threat vectors? The first 911 call that was made in the United States.
You don't have it in stock.
Okay. Yeah, we have a caller.
Which one is this?
Someone that's got separate phone calls.
No, which prescription? I'm sorry.
Whoever's talking to their pharmacy, please put your phone on mute.
Okay, so when do you think you can get it in? Oh, that's fine. That'll work. Oh, absolutely. And you know what, sir? When you get that, Phil, can you mail that one as well?
Oh, wait. I'll wait here just a second.
Okay. That's. I'm sorry.
Elena, you should be able to mute anybody as the organizer.
Yeah.
Judy,
Yeah. Mel. Yeah, that's fine.
Is this person?
All right. Thank you. All right.
Can
Bye bye.
Causing the disruption.
Whoever was just on the phone, basically with their pharmacy, would you please go ahead and mute your phone? Thanks, appreciate it. So the reason that the next gen 911 conversion actually ends up being a significant change in resilience is the fact that E911, first phone call with 911 was made back in the 1960s. So the first phone call was really over legacy technology, legacy communication systems, which a lot of people consider to be, or some people consider to be more resilient, more reliable than anything we've got today. But the reality is everything that was done in the early days was done in a spoken hub model. Spoken hub model, the issue you've got there is, for the most part, all of us are on the last mile. And while the backbones and the core networks of spoken hub networks are designed to be very resilient, the problem is if you either lose your hub or you lose your spoke, you've lost your communications. And most of the outages that were just described in that last slide were based on that. So NG911 is based on Ethernet, or based on data network technology. So it uses some Ethernet rerouting capabilities, some IP rerouting capabilities. And the bottom line is it's possible in the NG911 to build systems that will allow calls to automatically be rerouted to a different facility that's up in the event of an outage. So in the old days, we used to talk about reliability, 5 nines and that type of thing, which is great, but 5 nines are based upon a single incident causing the outage. The reality is, for large disasters, there is no single issue causing an outage. So it really becomes now more a matter of resilience more than reliability. We can also now, with NG911, we have the ability to remote calls to areas that are no longer limited within our call center. So again, legacy technology, usually it was hard to reroute calls outside of a call center, which meant that something like New Orleans that might have 20 or 30 call takers in their call center would really have to go ahead and reroute calls to possibly a local parish. Most of the local parishes surrounding New Orleans probably have got 1, 2, maybe 3 call takers at any one given point in time. So now with the newer capabilities, Dallas, for example, could reroute their calls to Houston, where they're dealing with dozens, if not over 100 call takers in a single call center. So 911 conversion is a part of it. But next generation 911 creates another issue. And that's it. When I looked at the platforms, I looked at the architectures of the olden days, I pretty much would, with AT&T or Verizon, you pretty much would either have Nokia or an AT&T Lucent platform. And everything from ingress to egress of the network was all done by one manufacturer. Interoperability wasn't a major issue. Today, if you look at next-gen platforms, you might have, if you've got 4 devices in the chain of a call, you might have 4 different manufacturers involved. So that's where we come into interoperability testing. We're currently working on a project with CIRI to create recommend the creation of a test suite to where, in essence, vendors can test against the standards. And testing against the standards is really the first phase or the first step of doing interoperability testing. The second step then becomes that of end-to-end testing. And then there's the issue of facilities resilience. And now again, with IP-based networks, you have the ability of using protocols like BGP, which have automatic rerouting, ESRP, well, there's a number of, I'm sorry, I'm drawing a blank there quickly, but there's a number of other protocols that are used for automatic call routing in IP networks, and even on the lower layers like Ethernet. So expanding tree, for example. So you can use those technologies automatically to reroute, but that's dependent upon your facilities being resilient. Again, if my primary line and my secondary line are basically in the same fiber cable, the likelihood is if that cable gets cut, you're going down, even though you've got redundancy. So the next part of it then is looking at doing assessments or analysis of who are my service providers, but more importantly, what are the underlying relationships that they have with other service providers that are providing their service, so that really what you're looking for is there a point of convergence to where you think you really have redundancy, but you really actually don't. Next slide. This is kind of the continuum of interoperability testing. Starts on the lower left with conformance testing the standards, and then end-to-end interoperability. And then you're looking at end-of-life issues. For example, device A is connecting to device B, and device A is end-of-life and basically no longer supports certain capabilities. Well, how does that impact your overall performance? And then you basically then have your post cutover, and that's looking at the life cycle. So that is, that's kind of the continuum. The House put together a study after Hurricane Katrina, and one of their findings was that massive interoperability had the biggest effect on communications, limiting command and control situational awareness of the federal, state, and locals, being able to address unsubstantiated and inaccurate media reports. So interoperability is pretty much identified as a significant issue, and as we get more of a heterogeneous network and away from homogeneous networks, that's going to continue to be an ongoing problem. Next slide. Okay, NENA, for example, recommends multiple broadband services out of each PSAP. I know that can be a real challenge in a lot of areas. We've got areas of the country where there's not one broadband connection available, let alone multiple broadband connections. But again, to the best effort that you can apply, looking at redundancy and resilience as opposed to individual reliability. And I think we've already really kind of talked through the bottom parts of this slide already. So next slide. And like the other speakers, other presenters, I will hold questions till the end. Thank you.
Well, thank you so much for that very focused brief on NG911. I know from personal experience using the E911 capabilities of my phone down in Puerto Rico, I was able to make Wi-Fi calls through the system we created through the satellite comm link. So it was really important when you don't have cellular capabilities. So looking forward to NG911. All right, for our next brief, we've got Junaid Farouk and Kwayan Zhu. Thank you so much for being here.
Good afternoon, everyone. My name is Junaid, and I'm an assistant professor at the University of Michigan in Dearborn. I'm delighted to be part of the panel today and to share some of the work that I and Kwayan from NYU have been doing recently. Our work is related mainly to the risk analysis in critical infrastructure systems from a supply chain angle. Next slide. As we have heard from some of the earlier panelists, that future cities are going to be smart, which means there will be more and more connected as well as autonomous. And this is being fueled by advances in communications technologies like the 5G and the Internet of Things. Because of the massive connectivity coupled with interdependencies between multiple infrastructure, the security risks also get cascaded and amplified. So it's really important that these systems, which are networks of networks, so to speak, are made secure and protected from attacks and malicious actors. We've seen that a lot of emphasis is generally paid on cybersecurity, authentication, and physical asset protection. But one thing that is less talked about is the supply chain security. And that's an extremely challenging problem to deal with. Next slide. When we talk about IoT systems, they are not standalone or isolated. In fact, they are actively interacting with other devices and performing sensing and actuating tasks. And if we dig a little bit deeper, we can see that any typical IoT system broadly involves an integration of several different components. So there are endpoint devices which have some firmware or software running on them. And these devices then make use of some communication networks. Communication networks itself usually have many, many different layers. So the devices use these networks to connect to the internet and to the cloud infrastructure. And then at the other end, we have user devices that view and control the operations. So in this value chain, we see that there are multiple services and functionalities involved, which are provided by many, many possible vendors. Some of them might be malicious or may intentionally misuse their capabilities. We've seen examples in the recent past where 5G vendors were allegedly involved in data theft and spying on sensitive information. So the bottom line here is that there are many entry points of attacks in modern 5G and IoT systems that can be exploited by malicious entities. Next slide. So supply chain attacks can be of many different types depending on whether it is related to hardware functionality or software functionality. If we just talk about software, there are possibilities where the software building tools are compromised, the code sign certificates are stolen, or even there's malicious code written somewhere in the firmware. Similarly, hardware may also have additional chips or circuitry to perform malicious. Generally, the measures that are taken to deal with such attacks is to have policies for ensuring code integrity, having detection tools for such functionalities, doing regular updates and patch distributions, and finally having an incident response process in place. Because whenever an attack happens, we have to deal with it by updating our systems and disseminating that information to customers and users. But despite these measures, we continue to see supply chain attacks happening, and more so recently. Next slide. The primary reason for this ineffectiveness is that the supply chain is a very convoluted problem. There are cyber and physical components intertwined in a complex fashion. So the vendor involvement map is quite complex. Then the supply chain is also dynamic because vendors may merge other vendors or get acquired by others. So it's very difficult to keep track of what the vendor hierarchy is and what the relationships are. And more so, the complete supply chain may not even be known to the end users. So mapping out the supply chain actors may not even be possible. Finally, there's the lack of available tools that can be used to make decisions when it comes to selecting suppliers for the first time or upgrading vendors in the middle. Next slide. So to tackle this challenge, we've been working with CIRI towards ensuring that we have trusted supply chains in our ICT and IoT infrastructure. The first aspect is risk assessment. This is important because we have to quantify how risky the system is based on trustworthiness of the vendors. So we're working on analyzing the vendor risk, on a system process flow. This is going to be useful in ideas such as cyber insurance, where the risk can be transferred to some external entity based on our assessment. Then we are developing techniques to identify which components of the system are most risky, meaning that they can have the most impact on its operation. So from there, we can actually backtrack to the specific vendors that are causing risk. We're also developing tools that can recommend which vendors to select when a new system is being deployed. And similarly, it can also recommend which components to upgrade based on vulnerability reports that keep coming out in the future. Finally, I believe there's going to be a lot of regulations and policies in place for vendors in the future. So as part of this project, we are looking at tools for compliance checking and policy implementation on such IoT systems. We're working with industry partners, and we have support from cybersecurity firms to see this capability being developed. And I think once developed, these tools will be good for both government and private sector organizations who do not have the capability to do risk analysis once new cyber and supply chain attacks are discovered. So I think there will be a lot of exciting stuff and new developments that will come out in this very important area. But for now, I just want to thank you all for your attention, and I look forward to seeing your questions. Thank you.
All right, thank you so much. That was a great overview of the supply chain risks. All right, that leads us to some questions. I've got a couple. Let's start off, and we'll start back at the top with EMP. Glenn, on slide 3, you talked a little bit about, the low probability and high consequence, and that means that there was maybe a composite risk analysis that had been conducted. And how can we best conduct some type of an impedance match with preventative methods or measures in order to prioritize maybe the best tech to either harden the infrastructure or accelerate the recovery time for those affected systems?
Can you repeat that first part again? I'm sorry, there was some noise in the background that disrupted me.
Yeah, let's go ahead and do an all call. Can everybody mute their mics for us? We've got some kids in the background that we're hearing.
Can you go ahead and ask that question again, please? I'm sorry.
Can you hear me now?
Yes.
Yeah, how can we match preventative measures in order to best prioritize best tech to harden the existing systems and also accelerate recovery time of affected systems?
Well, that's a really challenging question. And that's what we're trying to do with our tool. As I mentioned, we can't test every possible scenario. There's just too many scenarios to test, especially since you have such large uncertainties in the operational conditions, et cetera. And so we're trying an approach to this where we do it through a statistical analysis where we're looking at the coupling all the way down to the circuit level where we can get a metric of performance. And what we're trying to do with that then is sort of rank and prioritize things. And so we have uncertainty in our codes, and we can sort of look at the performance metric and say, okay, here's the potential impact. And if the potential impact is extremely low, we can just skip those and focus on the configurations or scenarios where the impact is potentially higher, and then focus our attention on those specific cases, whether we do testing for that or surrogate testing for that or more detailed analysis. we want to try to prioritize, if you will, where to focus our energy. And likewise, with the mitigation techniques, we can do the same thing. We can apply a mitigation technique. We can protect against EMP if we want to, but it's just too costly to protect every system to the level that you need to do it, or a default level, I should say. We only want to protect them to the level it's needed. And so we can, once again, look at a mitigation technique, do a sensitivity analysis on that, and then focus our attention on those areas or those systems that are more vulnerable, and then address those. Does that answer your question?
Yeah, it gets there. I guess, with your statistical analysis, is that sort of a mod simulation environment where you're analyzing it virtually? Because it costs quite a bit to do the test and evaluation in the open and run those tests in the real world. So
it can be actually a combination of both. In our model, we break things up into a hierarchy of models, if you will, and those models can be either test data, they can be ideal transform mathematical formulas, they can be actual numerical codes. The computational effort required to model this is beyond what we have the capability of doing. And so we have to break it up into components that we can model. And we can make assumptions along the way, worst case assumptions, if you will. And if this is 100% for everything, then we can start refining those assumptions and adding in detail where we need to. And that, like I said before, that detail can be either measured data, it can be model data, it can be numeric data.
We do have a question in the chat for Glenn, really quickly, sorry. Since radio waves cannot transmit through water, how EMP, EMI behave through water? That's from Yufang Lin.
Yes, that will actually provide a good shield. And so if our electronics were all underneath water, they wouldn't be affected by EMP, but we would have other challenges associated with that. So, and that's effectively what we can do with EMP mitigation, is that you shield from direct radiation, and then any type of cable that you have coming into your system, you put protection on those cables. Those are two standard mitigation methodologies.
yeah, so I guess a follow-up to the mitigation strategy, is this sort of a Manhattan project size problem, or can individual agencies pursue their own strategies? Considering all these dependencies and the technologies, it seems like a general solution seems almost insurmountable by one organization. So I guess the question is it has to be a larger national effort.
I think so. I mean, I think it comes down to trying to develop policies that are practical to implement, and strategies to mitigate, an effect if it should happen. Some of that can be done. We have different mill standards for equipment, for example, and so having different standards for electronics that they have to survive certain environmental conditions, electromagnetic radiation conditions, is one way of doing that. As we change technologies, it also helps as well. In some cases, for example, the move to fiber optics helps tremendously, because the fiber optic itself is not susceptible to EMP. And so some of the 5G systems, that's very useful. The communication lines are not susceptible to EMP. The power lines, however, that still go up to the transmitters and the receivers, are still susceptible to EMP. Right. Yes, I think it does require a national effort to coordinate this. I think that's why you see the executive orders coming out, right? Requiring the agencies to work with each other to solve this problem.
Right. And then, when you start doing some of your statistical modeling, what kind of cascading effects on the communication system happen? You have some of your, from the antenna, to the equipment, to the routers, to, where's the best places to put our money to shield? You mentioned the fiber optics, but I guess the actual components of the router and switches, but what other cascading effects happen downstream that we should be worried about?
Well, that's the exact purpose of our program. So I don't have the answer for you today, but that's what we're actually trying to investigate. Is we're creating a model to be able to come up with those statistics and look at where it's best to focus our mitigation efforts.
Alrighty. All right, so let's move to the next slide deck for next generation critical infrastructure. You know what? I guess this is to Karthik. Which are the following emerging technologies would best represent the best hope for the next generation critical infrastructure, or does it have to be a mix of all to address all those risks?
Well, that's a really good question. It's got to be a mix of technologies, right? Meaning 5G and things are happening, cloud is exploding, and IoT is exploding, where it's no longer a phone. You know, our Fitbits and all kinds of IoT devices start communicating. Even homes start communicating. Nest, who knows, the next version of Google might say, hey, we have not seen activity in the home, but we know people are here, and it may start sending stuff that we don't even know about, that nobody's here, or, you know, all kinds of, maybe, and we've heard about how Alexa is listening, and then therefore, you know, maybe it'll start sending something out, right? So we don't know. So we got to look at all the different things and say, how can somebody spoof that? You know, can somebody do something? So yeah, I think, you know, it's probably a combination of multiple technologies that we have to look at from a threat vectors perspective and see how we can detect them or make sure the integrity or the confidentiality of the message and the recipient is validated.
Excellent answer. Should we, for the ECCs, the emergency communication schools, and the PSAPs, should we be adding some type of an additional capability? It seems like there's a little disjointedness to how those work right now and how they're across the system. Should we add something like a SAR emergency beacon to phone systems for emergency location for people? Would that be something that we'd be thinking about, or is that in the works?
No, that's a good question. I mean, I'm not aware of a SAR type capability coming into the telecommunication chain, but I think it makes sense to have the search and rescue type beacons maybe in the cell towers. And so then you now have a geolocation from a cell tower, maybe that's already coming through the phones anyway. But and obviously then we got to worry about that not being spoofed, right? So it's got to be something that cannot be, the integrity cannot be violated. The question might be, you know, when it goes into billions and billions of devices, is that practical to have them in every device or every type of asset? And then how, you know, would that become a chatter and noise? So yeah, I mean, there's probably a nuanced way of looking at it to say maybe not everyone, maybe there's a way to aggregate it so that you can, you know, bring it down to a certain restricted, you know, size or footprint that you know you need to go look for from a search and rescue perspective or, you know, whatnot. But that'll be something interesting to certainly look into and see what that might look like, or, you know, how can that be added?
Yeah, Joe, this is Walt. Let me add to that too. Yeah, let me partially answer that question. So there's a whole lot of work being done right now in the location-based space. So location initially, you know, with E911, the first version, there was no location, and with the next version of 911, it was added, and then they added wireless. The wireless added triangulation off of the towers, which basically looks at direction, power, and timing parameters to determine the location. The problem is that's really only accurate. FCC pretty much requires within about 50 meters. So what's been happening lately is they're adding additional information that does what they refer to as assisted GPS. So we go ahead and we use GPS, we use the triangulation, but in addition, we use an awful lot of other capabilities that are built into the smartphones. And the desire ultimately is to get that location down to 1 meter. So when a person does call in via 911, you basically have got a 1 meter accurate location. Now that is very, very, very difficult to do, but in essence, the concept that they're using to do that is a combination of every other algorithm that they've got out there today, but then also using things like, you know, folks like Google end up driving all over the country and look at the locations of wireless access points. So they do a wireless access point identification and says, okay, well, when the Google vehicle was here, it looked like they could see these 3 access points, so that must be where I am. But what they're also doing though is they're taking all that information, putting it into the smartphone, and then letting the smartphone do the location calculations. And then so that's fed over the network back into the device. But again, everything that you can do can be spoofed. So that's where the security aspects of all of that end up coming into place. You know, there are people now, even at the military level, that are basically spoofing GPS. So they're sending out false GPS information to get devices to think that they're somewhere where they're not.
Right, right. And in the case of Puerto Rico, when all the cell towers were down and there was no power, folks were trying to use their phones, of course, but they didn't have any access to any communications or power, not even to charge their phones. So, you know, one idea would be some sort of star beacon for satellites to pick up, right? Or maybe you couldn't do HF, but something in the higher VHF or UHF frequency ranges. So just some food for thought. Just trying to think, you know, if the infrastructure was hit by a natural disaster or an EMP, and you're trying to get emergency services to folks who really need it, you know, that was the big issue in Puerto Rico. We just couldn't find people who were having issues because the communication networks were down. So it was increasingly difficult. So okay, so that's a good discussion.
I'm sorry, pardon me, Joe. Dan J, did you have a question? I saw you come off mute and then you went back on. Okay, proceed, sorry.
Yeah, and so Karthik, you said more needs to be done. And so is this sort of a Manhattan Project size problem as well as, you know, the cyber resiliency of our 911 systems and our critical infrastructure? Is that raised to that level? I think it does. Seems like we have a lot of these Manhattan-sized problems, and it seems like it's just getting worse.
Yeah, no, but again, good question. From what we've seen so far, right? It's not necessarily one and done. Like, it's not like you have an answer and then the problem is solved. It's more like the CDM model that DHS has, because PSAPs are living things. New technology comes in, the equipment comes in, procedures change, technology is changing all the time. And so the security posture of where you are today will certainly change in 6 months when you buy in a new equipment, or a supplier changed, or your procedure changed, or you get merged and you go somewhere else. So all of these people, process, tools changes affect the security posture from a cybersecurity perspective. And so the more needs to be done was really to understand in one side, the PSAPs are moving away from the legacy copper line, telephone line, based things to a hybrid and ultimately to an NG911 model. So they are changing with the technology stack and the architecture. And then separately on the other side, because of that, people are no longer just using landlines or cell phones, but now smartphones and texting and SMS and videos and chat, and maybe even maybe you can start tweeting, I need help, who knows, right? There could be other ways by which the communication starts happening. And so this is a living system or an ecosystem. So the recommendation, what we're hoping for, is to have some kind of a continuous monitoring, diagnostic kind of a way whereby the PSAPs can go through a process, do a self-assessment, or some help is given to them, and then they understand where they are. And then as and when changes happen, they can go continuously keep an assessment of their security posture, whereby both they know where they are as to what their threats are, what their cybersecurity risks are, and then do risk management accordingly. But collectively, DHS, as the national, for the Homeland Security, can look at this hopefully at some point and say, hey, this is the security posture of our 911 emergency communication systems. These are the vulnerabilities. So we need to be able to look at it holistically and be able to give them the help that they need nationally so that we can address this problem, et cetera, et cetera. So we would probably look at it more as a cyclical thing that feeds on each other and improves quality over time. It's not necessarily a discrete step that you do and then it's solved.
Right. Hey, Walt, when you were talking about the NG911 conversion, enhanced capabilities such as ESRP, can you explain that just a little bit more and go a little deeper into that?
Sure. So when you look at the, you know, if you look at the way E911 evolved, again, basically they just took existing systems and they built E911 around existing capabilities. Fortunately, with NG 911, what happened as it was being built from the ground up, they were looking at how do we make it better. So one of the devices, one of the servers or proxies that was built into it is called an ESRP, Emergency Services Routing Proxy. So in the process of the call going to the right call center, there's a server in the middle that it's in essence, it's a policy engine. So a call could basically would go into this policy engine before it's routed to the call center. It can do intelligent-based call routing. So it, for example, could look at it, say, all right, looking at the call, I see this call is flagged as a person that speaks Farsi. So, and if nobody at that PSAP speaks Farsi, what it would do would be to automatically reroute it. It would be skills-based routing. It would reroute it to another PSAP where somebody did end up speaking the language. The same policy engine can also be used to deal with congestion issues. I mean, if you can kind of imagine again, as you know, again, as the bomb hit Nashville, I'm sure that 911 call centers were all completely overloaded. How do I take those calls and then distribute them across the serving area, or do a complete reroute in the advantage of a complete outage? So I've now got an indication that, by the way, the New Orleans call center has been just shut down. Where do I route it to? So those kinds of things that really build more intelligence into the whole architecture from the ground up are one of the reasons that doing an NG 911 transition at the end of the day basically gives you more reliability, more resilience.
So that interoperability testing is going to be really critical to kind of pressure test the system to see if failovers in these other call centers will pick up that routing. Is that correct?
Oh, exactly, yeah. I mean, you know, there's about 6,300 PSAPs in the country, according to some Department of Transportation and FCC reports. With that many call centers, you can imagine, and I would guess that there probably are about 15 to 25 or 30 different companies that manufacture the call center systems. So, you know, if you look at, for example, text messaging to 911 centers rolled out kind of sporadically across the country. You know, it wouldn't be good if all of a sudden I'm working with my call center and my call center has capabilities A, B, and C, but because of different technology, different vendors and everything else, my call gets rerouted, and all of a sudden the capability that I thought I had is no longer there because, well, my PSAP has it, the upstream PSAP doesn't have it. So making sure that, you know, you look at all of the standards, you understand what all of the pieces of the architecture contain, and then making sure that the system conforms with that. Now, not every vendor is going to conform with every feature and capability, especially in the early days, because, you know, they typically roll out these capabilities as their customers demand. But it is important that the end customer be able to look at the type of conformance testing and say, all right, I see my system does this, and it's been tested and it's proven, and my system does that. It doesn't do the other thing, but the other thing really doesn't apply, so it doesn't matter to me.
Right. Yeah, that's a good topic for discussion for sure. And that kind of leads us into this whole supply chain risk of making sure you're getting the right capabilities and making sure they're resilient. So I guess, you know, if we have a multi-layered, you know, cyber physical supply chain risk analysis done, and this is for you, Junaid. I like your IoT ICT value chain, but how can we strengthen each link in the chain? Can we use things like blockchain technologies to secure those links? I mean, what kind of technologies inside each one of the links and separating those links and making sure that the whole chain is secure.
Right. So the value chain has many different components and they come together and form the entire system. So we want to make sure that each of those blocks in the value chain have a secure supply chain. And blockchain is one such technology which can help us ensure data integrity, and certainly it can be used to ensure the supply chain of individual blocks, and to make sure whether these devices or components within those blocks are counterfeit or not. So, but again, blockchain has its own issues. So it would be interesting to look into and see whether it would be a practical solution in the problem that we're trying to solve. But I would say blockchain may only be partly useful because the problem is much more complex. We are not only trying to ensure integrity of the supply chain itself, but also we want to test the functionality of these blocks and to see whether there is something malicious going on. And there's another thing that comes into the picture, which is the trust of the suppliers and vendors. So all those things have to be looked at holistically. And as you said, blockchain may be one small component of it, but it cannot solve the entire problem.
Yeah, that's right. Now, when you undergo your analysis of the entire supply chain, what type of tools are you using, or are you creating a tool to support that analysis?
We're actually creating our own tools because the scale of the systems that we're looking at is very large. So even though there are tools available commercially for supply chain analysis, because supply chain is an old problem and it's very relevant in manufacturing and whatnot, but those tools are not very useful in the problem we are solving because it's much bigger and much more complex. So there's a complex web of supply chain actors, and then there's a complex interaction of components. So all of this combined together becomes a very complicated networks of networks scenario. So we have to develop our own metrics and tools to deal with that.
Yeah, for sure. You know, you could take the automotive industry as an example, where you have the OEM who is, you know, the main integrator of all the tiers below it, you know, tier 1, tier 2, tier 3, and all those suppliers. And it's just an overwhelming problem. You could use some graph theory to actually and have a graph database to analyze how a part gets made, everything from the development cycle to the testing and the integration, all the way up and through until it gets to the vehicle. That's a Herculean effort to try and understand the supply chain risks associated with all those ECUs that get built to be put into a vehicle, where you have over 100 of these ECUs in a decent vehicle.
Yes, so we're trying to break down this complex problem into smaller chunks and then solve them and try to put them together and try to find out meaningful decisions and solutions from those.
Yeah, that's another one of those hard problems. That's a tough one for sure. Do we need better models to help predict where the weaknesses are? So when you design your tool, are you going to use any type of machine learning model to help predict where weaknesses might lie in the chain? So if you found some type of a threat or cyber physical action that was done, could you replicate that in the machine learning model and apply it to your model? It's just an open question.
Yeah, certainly we would like to make use of the advances in machine learning, but the biggest challenge here is we do not have a lot of data available publicly on supply chain, and we only have a handful of cyber supply chain attacks, and even those data is not publicly available. So obviously we like to have machine learning capabilities, but at the moment it is hard. and I think we are focusing on models and trying to use them in decision making and optimization frameworks. But as we have more and more information and data available, I think we want to incorporate that into our decision making process.
Yeah, for sure. All right, so those are some of the questions I had. Maybe we could open it up for others to go ahead and verbally speak some of the questions they might have for our panelists. Don't all go at once. Yeah, going back to the automotive, idea, it doesn't help that the automotive chains or supply chains are very highly, they're held tightly because of the new versions of car coming out, because those are very tightly held. So it's interesting that it's very difficult to get supply chain data for sure. Maybe we could work with Amazon or something like that to understand their supply chains and maybe they open up some of that data, and possibly do a challenge.gov and get a Kaggle competition going on that supply chain data. I think that would be pretty interesting.
Yes, I think it's going to be very useful.
All right, any questions out there? Come on, you all must have one question at least. All right, well, I would like to thank our panelists. They give everybody a round of applause, please. Thank you so much for coming and attending. And thanks to everyone who did come and attend and muted their mics. Randy, off to you.
Thank you very much, Joe, and thank you for hosting and moderating this panel. We really appreciate it. And thanks to everyone who joined us. Sorry about the little bit of the background noise initially, but we finally got it worked out. So thank you very much. Appreciate your attention and appreciate you joining us today. Thank you very much, everyone.